Okay, morning everyone. So there's 13 people out of 28 so far. I just want to double check whether you can hear me. 14, 15, 16, 16 out of 28. Please let me know if you can hear me. Okay, please let me know. Or if once again you hear the sound of the fan yang macam ribut taufan itu, tolong bagi tahu lah. Okay, but please open your textbooks to subtopic 6.2. Okay, subtopic 6.2 in your textbooks. Okay, and then we will start. Okay, so today we're going to continue our study on light and optics. Okay, by looking at this thing called total internal reflection. Okay, so previously we have looked at what reflection is about, and reflection is probably the easiest thing in the world. Okay, reflection, we've seen this before. So if let's say you have a wave and it hits a surface, okay, it hits a wall, what's going to happen is the wave is going to go here, and then bila dia terkena ini dinding, then it will be dipantul kembali. Okay, so this is what we call reflection lah. Okay, the standard reflection. And we also learned that if the wave, let's say for example like this, okay, this is the wall or the mirror or whatever surface now. If the wave comes this way, okay, we find that bila dia pantul balikkan, it will pantul balik with the same angle as the angle of incidence. So this angle and this angle is the same. Okay. So in reflection, okay, I equals to R. The angle of incidence equals to the angle of reflection. So if this is a wave like this, okay, then you find that the wave also continues back the same way. Okay, but in this subtopic, we're going to discuss something that is very specific to light waves. Okay, when we talk about light, okay, so light has this interesting characteristic. Okay, it's this interesting phenomena which we call total internal reflection. Okay, now to understand how total internal reflection works, let's take a look at this picture. So you see this is a picture of a kura-kura or labi-labi or tortoise or turtle. I think it's a turtle. Okay, but you see, notice that you can see the image of the turtle, okay, on the surface of the water. Okay, this is an example of how total internal reflection looks like, because it is reflected back towards the turtle. Okay, if you think about it, okay, if we study in the previous chapter, if this is the turtle, okay, yeah, I know, weird looking turtle, fine. So if this is the turtle, whatever light that goes towards the surface of the water is supposed to be refracted, because this is more dense to less dense. So it's supposed to be refracted. So if it is refracted, okay, then by right, there shouldn't be any reflection. Okay, sepatutnya tiada reflection lah, sepatutnya dia semua kena refract kan, whatever picture that, whatever light that comes from the turtle is supposed to be refracted. So why is it that the turtle can see its own reflection okay, on the surface of the water? Okay, on the surface of the water is because of this phenomena which we call total internal reflection. Okay, now total means the entirety okay, every light is reflected back. Okay, so if whatever light that is here is not refracted, but it is reflected back. Whatever light is here is reflected back. So total. You don't see half a turtle. You see the whole turtle. Okay, that turtle and total. Okay, you see the whole turtle. You don't see half a turtle. Secondly, is internal because it comes back towards the original source. Okay, it's internal. And reflection because it is reflection. Now, to understand how this works, we need to take a look at the simulation that we did that day. Okay, the experiment So that day when we were doing this, okay, so everybody knows this Okay, so we've done this. Can you see this? Okay, so the day when we were doing this okay, so you had this we start from air, then we did glass, kan? Okay, so fine, let's do glass. So when you turn on the light, this is what happens lah. Okay, at any particular angle, I'm going to put the thing over here. Okay, so at any particular angle, okay, for example 30, and then you get about 20 degrees the refracted angle. Okay, but you see the thing is there is this light over here. Okay, so this one we know. Okay, this is the incident angle and this is the refracted ray. This is the incident ray, this is the refracted ray. But what about this over here? Why is there a line that is going back over here? Okay, that is because any border, okay, any sempadan lah di antara dua medium, okay, actually acts as a surface. So yes, most of the light is actually refracted, but there is some light, okay, there is some light that is being reflected back over here. So sini adalah reflection, sini adalah refraction. Okay, because no choice. This X, okay, this border over here, okay, that you see, the border acts as a surface itself. Okay, most of the light goes through the border, but some of the light, okay, gets reflected back. Okay, sepertinya kamu letak satu cermin di sini, it will get reflected back. If this was a total cermin, then obviously there will be no refraction lah. It will be all reflected. Okay, but this is because there's two different mediums. Okay, one from air going into glass, so most of it will be refracted, but some of it will be reflected. Okay, that's the explanation for why there is a little bit of light lah. Okay, if you see over here, there's a little bit of light. Okay, let me reverse the situation around. Let's say I want to travel from the glass into air. Okay, from the glass into air. Now we know that glass is more dense. Okay, more optically dense. Glass is more optically dense, and air is less optically dense. So more to less, it will be refracted further from the normal. Okay, and of course there is this reflected. There's some reflection over here. We call this internal reflection. Okay, this is internal reflection because it happens in the glass, in the glass itself. Okay, now what if I increase? Notice what happens if I increase the angle of the incidence. Okay, of course, if I decrease, then the angle of refraction will decrease lah. But if I increase the angle of incidence, notice what happens to the refracted angle. It will be refracted more and more towards the normal until a certain angle where there is actually no more refraction. There's no more refraction, and everything after that is all reflection. So we find that this is what we call total internal reflection. Total because sebelum a certain angle, okay, before a certain angle, this is just internal reflection. It's not total, okay, because there's still some refraction going on. Okay, but after a certain angle, okay, take a look at this, and notice what is the angle where the refraction totally disappears. Okay, so increasing it slowly. Oh. Okay, so about about here lah. Okay, this is about 42. Okay, about 42 degrees. Okay, so at 42 degrees Celsius, when the incident angle is about 42 degrees, that is where refraction stops and reflection, and only internal reflection happens. And that's why we call this total internal reflection, because the light is supposed to be refracted. The light is supposed to be refracted and only some minor internal reflection. But after a certain angle of the incident angle, we find that there's no more refraction. Okay, in this case, it's about 42 degrees. Okay, there's no more refraction. There's no more refraction, but everything is totally internally reflected. That's why we call this total internal reflection, because there's no more refraction that's going on. Okay, normal situation, there will be refraction. Okay, now this works, this works under two conditions. Okay, number one, number one, the light ray must travel from an optically more dense to less dense. This is the number one. Higher refractive index want to travel to lower refractive index. If let's say I change this around, I do air and then over here glass. Okay, sorry, glass. Okay, so this is less dense to more optically dense. Less optically dense to more optically dense. No matter what I do, okay, it will always be refracted. Okay, there will always be refraction. I cannot do total internal reflection if it is going from less to more. Cannot. So the first condition is that the light must be traveling from a more dense to a less dense. This is more dense, this is less dense. Okay, that's the first one. Then I can do, that there can be some refraction, and then after that there'll be total internal reflection. Okay, even if I change to another one, let's say water lah. Okay, also can. You see, this is refraction, and some reflection. But if I increase the angle until a certain angle, okay, so this angle is about 30, 40, 50, 50 degrees. Okay, so 50 degrees, then you will be, total internal reflection. Okay, even if I were to use the mystery block, same thing. Okay, before that is this one. But look at this, this is a very, very high total internal reflection. Very high refractive index lah. Because you see, the angle is so small. Just now, glass was 42, right? Water was 50 something. But look at this one, this mystery block. This mystery block, the angle where it becomes totally internally reflected is about 10, 20, 25 degrees. Okay, mystery B, you have to increase some more, so it comes about here, like this. Okay, so it's about 30, 40, 47 lah. Okay, about 47 degrees. So we find out that different materials lah. Okay, different materials have different angles where the refraction stops and the total internal reflection happens. Okay, so as I said just now, the first condition, okay, for total internal reflection to happen is that the light ray must travel from a more dense to a less dense material. That's the first condition. The second condition is the incident angle, okay, this angle over here, okay, must be more than a special angle. Okay, so just now, okay, this angle, as I say, 47 degrees. 47 degrees is where there is no more refraction and everything is totally internally reflected. So this 47 degrees, the incident angle where there is no more refraction and everything is totally internally reflected, okay, this angle is called the critical angle. I repeat, the angle where no more refraction happens, but everything is totally internally reflected, it is called the critical angle. Okay, it's critical angle. It's critical because that's the angle where everything changes. There's no more refraction. Okay, that's why we call it the critical angle. So the incident angle must be at least or more than the critical angle. Then the total internal reflection can happen. And as you have seen from this simulation, different materials got different critical angles. Mystery B has 47, okay, about 47 lah. Mystery A, I need to write this down somewhere. Okay, mystery A is about, let me see, how much did I say just now? 25. Mystery A is 25, mystery B is 47. Okay, glass is about, how much did I say just now? 42. Oh, okay, 42. And water is even bigger lah. Okay, water is about 50. Yeah, 50. Okay, so different materials have different critical angles. Okay, because different materials have different index of refraction. Okay, so let's take a look at this. Okay, so what I need you all to do is, because I cannot do both at the same time, I need somebody to jot down what is the critical angle and what is the refractive index and what is the material. Okay, then after that, please type it out in the chat so that so that I can write it down in the PowerPoint soon. So let's start with this. Water is 1.33 index of refraction, and the critical angle is about 50 degrees. Okay, that's number one. Water is, you know what? Let me see if I can write it down. Hold on, hold on. Okay, so let me see if I can. Yeah, this is me trying to do everything. Okay, water is 1.33 and the critical angle is, how much was it just now? 50 degrees. Okay. Okay, second material is glass. Glass is 1.5 and the critical angle is, the critical angle is about 42. Okay, so 1.5, 42 degrees. This is glass. Sorry, I'm writing down on my PowerPoint. Okay, the third one is this mystery A. Okay, mystery A, the critical angle is about, let me see, 25. Okay, 25 degrees, which we don't know lah. Okay, mystery A is 25 degrees. And lastly, mystery B, which you all supposedly, you all already supposedly know what is the refractive index lah, because you already did the experiment, right? That's if you did. Okay, so mystery B is about 30, 45, 46? No, 46. Okay, 46 degrees. So mystery B is 46 degrees. Okay, so so remember the two conditions. Okay, the two conditions for total internal reflection is number one, the light must be traveling from more optically dense, glass, water, okay, to less optically dense. And usually, in our case, less optically dense refers to air lah. Okay, we talk about air all the time. Okay, and then the second condition is the angle of incidence must be bigger than the critical angle. Then total internal reflection can happen. Okay, so let's take a look at the data that we collected just now. Okay, so we have water. Okay, we have water where the refractive index is 1.33 and 1.50 for glass. And I'm going to give the letter for critical angle as angle C lah. Okay, C for critical. Okay, C is critical angle. Dalam bahasa Melayu dia dipanggil sudut genting. Okay, so dia sangat genting. Okay, titik genting lah. Okay, because after the critical angle, then everything changes. No more refraction. Everything is totally internally reflected. Okay, I want you to take a look at this relationship over here. There is a relationship between N and C. We find out that the bigger the refractive index, okay, the critical angle becomes smaller. Okay, now small critical angle, okay, when the N is bigger, okay, the bigger the refractive index, okay, the smaller the critical angle, and we find out that smaller critical angle means easier to reflect. Okay, it's easier, actually, it's easier to be totally internally reflected. Total internal reflection is easier, okay, it happens more often if the material has a smaller critical angle. But the critical angle is dependent on the refractive index. Now let's take a look at this mystery A and mystery B. If you just take a look at the angle, you can tell me already. Mystery A and mystery B, if we compare to glass, let's say, okay, mystery A would have a higher or lower refractive index than glass. Would it be bigger than 1.50 or smaller than 1.50? Okay, same thing goes with mystery B. Mystery B, since the critical angle is 46, okay, would the refractive index be bigger or smaller than glass? Okay, that's, if you can understand this relationship, then you know whether your gradient is correct or not. Okay, so if you take a look at this, since the critical angle for glass is 42, okay, so if you want a bigger, if you want a bigger if you want a bigger refractive index, you need to have a smaller critical angle. So that means this one definitely bigger than 1.50. Okay, how about this? This one, the critical angle is bigger than C. So that means the refractive index for mystery B is definitely less than 1.50, but only a little bit less lah. I think the answer is like 1.4 something, 1.47 maybe. This is 2.4 something. I think so. Okay, 2.6 or 2.4, I can't remember. Somewhere around there lah. But the idea is this: if we know the critical angle, we can guess whether the refractive index is bigger or smaller. Okay. Now remember, if the refractive index is bigger, means it is harder for light to travel through it. Okay, because it's more optically dense lah. Okay, more optically dense means susah untuk cahaya melaluinya. Okay, that's why the critical angle is very small. Manakala air, water, the critical angle is so big, So because it's very easy for light to pass through. So this relationship is very important. Okay, when the refractive index is bigger, the critical angle is smaller. It's a very important thing. And when the smaller the critical angle, okay, it is much easier to totally internally reflect. Okay, and we will come to the application in a while. And that's basically the entire subtopic in a nutshell. Okay, just by showing you the two conditions, how total internal reflection happens, and these two important relationships. Okay, so for total internal reflection to happen, light ray must travel from more optically dense to less optically dense. Okay, that's the first condition. Second condition, the incident angle or the incident ray must be bigger than the critical angle C. Okay, they are the critical angle because that's the angle where no more refraction happens. All will be just reflected. Okay, now just now we can see this and we can see this. Okay, but what we didn't see is this. Okay, so as I said, if the incident angle is less than the critical angle, most of it will be refracted, some of it will be reflected. So the refracted ray will be strong, the reflected ray will be weak. Okay, and after the critical angle, when the incident ray is bigger than the critical angle, everything will be totally internally reflected. Okay, there is no more refraction, no more refraction. But ngam at the critical angle. Okay, ngam at the critical angle, we find that the refraction, the refraction is 90 degrees. Okay, this is something that we couldn't see in the simulation just now because they didn't show it lah. Okay, and it makes sense lah because when you increase the incident angle, the refracted ray, the refracted angle will become bigger and bigger and bigger and bigger until it finally reaches this one. Okay, 90 degrees, and then after that, all will be totally internally reflected. It's as if this refracted ray and this reflected ray, dia bergabung. Okay, let me show you again. Notice that also when we were doing this one, look at the reflected ray. Okay, I'm going to use glass again. Okay, don't want water on glass. Okay, so when sorry. Okay, so like this. So when I have glass, right? Okay, so when I increase the incident ray, notice that this reflected ray is also increasing in angle because it still follows the law of reflection. the incident angle must be same as the reflected angle. But it is as if selepas itu semua berlaku, okay, when I increase this, okay, look at how the reflected ray and the refracted ray, look at the intensity. This reflected ray dia akan jadi lebih terang. Notice. See, it becomes more and more bright. Manakala this refracted ray becomes more and more dim. Okay, menjadi lebih malap lah. Okay, and it is as if they both combine and then finally becomes all totally internally reflected. Okay, I repeat. So look, everything becomes bigger. This angle of refraction becomes bigger, angle of reflection also becomes bigger. And it is as if after the critical angle, okay, we know that at the critical angle, okay, at the critical angle, actually, over here is the refracted ray lah. Then after that, it will be all totally internally reflected. Okay, which is basically what is happening in our situation over here lah. Sorry, okay, in our situation over here. As if this refracted ray and this reflected ray, diorang bergabung. Okay, after the critical angle, diorang bergabung and then they will become totally internally reflected. Okay, but to understand this is very simple. Before the critical angle, most of it refracted, some of it reflected. At the critical angle, the refraction is 90 degrees. Okay, it is, we say it travels along the boundary lah. Okay, and the reflected ray becomes stronger, sorry. Okay, this one we saw lah, the bigger the incident angle kan, the refraction becomes less and less, the reflection becomes more and more. After the critical angle, no more reflection, the reflection will be totally strong already. Okay, so the question is this lah, is there a situation where there is total internal or total external refraction? No such thing. Okay, no matter what happens, whenever light travels from a more optically dense to less optically dense, most of it will be refracted, but some of it must be reflected. There is no such thing as totally refracted and then no reflection at all, no such thing. But there is such a situation where there is no refraction at all, but all will be totally reflected. Okay, saya punya lidah mau terkial-kial sudah L reflection. It's like a tongue twister. Okay, so anyway, I hope you get this lah. Okay, the total reflection ada, total refraction tiada. No matter what, whenever some light refracts, some of it will be reflected. Okay, but for reflection, it is possible. It is possible for total reflection to happen, but the syarat is this lah. It must be traveling from optically dense, more optically dense to less optically dense. That is the syarat. Okay, if we travel from air to glass, it doesn't work. Okay, it doesn't work. No matter how you do, it won't work. Okay, you don't believe me, but let's. I mean, we can always give it a try. It's in this one anyway. Okay, so let me change the situation. Now I want to travel from air and I want to go to glass. Okay, so as I said lah, this is apa ini? This is incident ray refracted, sudah refract, and then some of it reflected. But will total internal reflection happen? Okay, fine. Let's increase. Increase. You see, the more you increase, it's harder for total internal reflection to happen. Okay, you know why? Because when light travels from less dense to more dense, the refracted angle is smaller than the incident angle. Okay, so no matter how you adjust this, you cannot get the situation, I mean, except for this, you cannot get a situation where it will be totally internally reflected. So this condition is very important. You must be traveling from more optically dense to less optically dense. Yang index biasan yang lebih tinggi, okay, for example, glass, traveling into water. This one possible. Okay, wow. Okay, so for example, this lah. This is more optically dense, 1.5, and less optically dense, 1.3. Sorry, okay. So Still can happen because dia punya syarat masih ada. More optically dense to less optically dense. Look, most of it is refracted, some of it is reflected. Notice that even the light now is so weak. Okay, as I increase the incident angle, okay, we find that the refracted angle also increase until a certain critical angle. Okay, critical angle, and after that it will be totally internally reflected. Okay, so that's the two conditions for this thing to happen. Okay, so everything else after this slide is just a repetition of what I've said lah. Okay, so we're just gonna go through these slides. All right, so when we talk about total internal reflection, this is the formula that we want to refer to. Okay, n equals to 1 over sine c. Now previously we have studied three ways to calculate the value of the refractive index. Number one is sine I over sine R. Kalau adalah ada sudut biasan dan sudut tuju lah. Okay, you have the incident angle and you have the refracted angle. Another one is the real depth over the apparent depth. Okay, the third one is the speed of light in the air over the speed of light in the material itself. Okay, C over V. So this one introduces us to another one which only involves the critical angle. Okay, if I know the critical angle of this bahan, then I know what is the N1. Okay, so let's take a look back at our this one. If, oh dear, okay. So we want to talk about our mystery A, mystery B lah. Okay, that all of you try to determine the refractive index by using the graph method. Okay, which is one way to do it lah. Okay, which is one way. So you drew for both of these graphs. Okay, which some of you still haven't given me the experiment. So what am I supposed to do? Go to your house and collect it from you, is it? Yeah. Okay, so sine I, sine R, then after that you had the graph over here lah. And after that you calculated the gradient. Okay, and you find that the gradient equals to the refractive index. Okay, so we can also use this critical angle, okay, to calculate the refractive index. Okay, so if the formula is n equals to 1 over sine c. Now, since we know the critical angle, we can count the n. Okay, so n equals to 1 over sine 25. And this will give us, oh, I don't know. How much is 1 over sine 25? So it's about 2.37. Okay, this is the calculated one. So the gradient that you calculated from this one should be about this value lah. About. Okay, not necessarily, but about lah. If you got 2.6, yeah, so my one was 2.6. Okay, but according to our calculation, it's 2.37. Okay, now what about the 46? So n equals to 1 over sine 46. So sine 46. So this one is about 1.39. Okay, so we can use the critical angle, okay, to determine the refractive. Oh dear. Okay, to determine the refractive index. Okay, as long as we know the critical angle. Okay. Oh dear. Sneezing on live YouTube. Okay, so yeah, anyway, if your value of the refractive index is different from my calculated one, don't worry, okay, just make sure that it is according to the gradient that you have already determined. This is kita determine from the critical angle. Okay, but I just want to show you another way to determine the refractive index. Okay, by using the critical angle. But again, this is on the condition that it is traveling from more optically dense to less optically dense. Okay, this is the condition. So this is something that we established earlier. The higher the refractive index, the smaller the critical angle. Okay, the bigger the N, the smaller the C. Dan dia punya urutan mesti begini ya. Critical angle depends on the optical density of the medium. Okay, optical density. Bigger optical density means bigger refractive index. Okay, so there's this activity in the lab which we want to observe lah. Okay, the total internal reflection in a water stream. So you have this bottle over here. You know what? I'm going to show you the video instead of this one. Okay, so we want to see that when we let go of the water over here, of course, water is going to flow out lah. Okay, but when we point the laser, okay, we find out that the laser will follow the direction of the water, which is very strange. Because if you point the laser forward, the laser should actually be just going straight back. So why is it that the laser beam follows the uh, the water stream? Okay, and of course we know this is because of this thing called total internal reflection lah. Okay, something happens to the laser in the water that causes it to follow the water stream, which is called total internal reflection. Okay, so I hope you can see this. So notice this, the laser doesn't go straight. No. It it follows the water stream. No matter what angle the water stream is, this one. Okay, so until there is no more water, then it will finally be, oh, alamak, tidak sampai sana pula. It's supposed to go straight lah. Okay, so I think there's another one over here. But this is the explanation. So I hope you can listen to the explanation though. Okay.
Bending the light using water. Cool science experiment with a laser.
Can you hear the explanation?
We've been taught that light travels in straight lines.
Can you guys hear the explanation? Sorry, I don't know. I don't remember whether I've done this before. Can you guys hear the explanation? Sorry, you can either message me in the live chat or this if you can hear the explanation, because I don't know whether you all can hear. I guess you all should be able to hear though. But okay, anyway, I'm just going to continue now.
Well, here's a cool experiment that'll prove that light can also bend, or so you can make people think. For this experiment, you'll need an empty water bottle, water, a screwdriver or any pointed thing, a laser, and a bowl. Procedure. Take the empty water bottle and punch a hole on the surface of the water bottle. Make sure that the hole is made in or around the midway of the bottle. Put the bottle in the bowl and fill the bottle with water. You'll notice that the water starts flowing out of the bottle through the hole. Now, using the laser, project the beam horizontally towards the hole from the other side of the bottle. Notice that the laser beam follows the laminar flow of the water stream, and the beam crashes down along with the water into the bowl. Explanation. First things first, in this experiment, technically the light does not bend. Observe the laminar flow of the water stream coming out of the bottle. When the water is in laminar flow, the water stream acts just like a fiber optic and carries the light. When the light beam hits the water stream, the laser light gets reflected inside the stream. Remember, the surface of water is reflective both on its surface and below the surface. This underside reflection of water is usually seen in darkly lit environments like a fish tank. When light leaves a denser material, in this case water, due to the change in speed, it will change directions. However, when a certain angle, called the critical angle, is reached, it reflects back. The critical angle is the smallest angle of incidence for which light is totally reflected. Total internal reflection is a phenomenon that happens when a propagating wave strikes a medium boundary at an angle larger than a particular critical angle with respect to the normal to the surface. The critical angle of water is 48.8 degrees. When the angle of the beam crosses the critical angle, the light does not go out of the stream, and total internal reflection takes place. At the end of the stream, there is a lot of turbulence, so the continuous reflection chain breaks or scatters down, and the laser light gets scattered. Because of this phenomenon called total internal reflection, the light appears to be traveling along with the water stream. Remember to like this video and subscribe for more cool science.
Wow, I like the way he said cool science. Yeah, anyway, so that's basically an explanation of why the water doesn't go straight, but it follows the stream. Okay, but if you think about it, it's like this lah. So when the light travels, okay, through the water over here, okay, and of course this is the water stream, right? So kalau kita ikut kita punya fahaman, when the light hits the boundary of the water and air, it's supposed to be refracted. Okay, we know this, but because it is hitting the boundary, okay, at an angle that is bigger than the critical angle of water. Okay, critical angle of water is 46.6 lah. That means this angle is bigger than 46.6. So what happens is it's going to be internally reflected. No refraction happens. Then when it is internally reflected, okay, once again now when it reaches this point over here, okay, it is still more than 46.6 degrees. So it will continue to be totally internally reflected. Okay, and this is what happens. So if this is the water stream, okay, the light travels over here and reflected, 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 reflected. So continuous reflection happens. That's why the light seems to be traveling together with the water stream. Now, one of the biggest applications of this total internal reflection, if you heard in the video just now, is this thing called fiber optics. Okay, and we use fiber optics in our internet these days. Okay, kalau kamu ada contohnya, if you have Maxis fiber optic or if you have Cellcom fiber optic, okay, sorry, diorang panggil apa? Maxis fiber or like high speed internet lah. High speed internet works on this, on these cables which you call fiber optics. Okay, because light travels very fast. Okay, light is the fastest lah. Light, the speed of light is 3 times 10 to the power of 8 meters per second. Okay, so data is carried okay, through these cables which we call fiber optics, and that's just one of the applications. There's many more applications. We use fiber optics in, for example, medical equipment. Okay, macam kalau kita pasang camera at the end of this one, then kita, we just insert it into a small hole. Okay, and the image that we see is traveled from the cable reflected, 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 sampailah ke the machine that interprets the picture lah. Okay, so all these are uses of fiber optics, and the group that is supposed to do the application of total internal reflection, I hope that you include this application in lah. Okay, fiber optics is a very important one, but it works along the same principle. When light travels into the sun, bila dia sampai di sempadan, it wants to go out and be reflected, but cannot because it is, it is coming in at a bigger than critical angle. So it will be totally internally reflected. Then it will continue to be totally internally reflected until it finally reaches the end. Okay, so what will happen if the water stream is replaced with oil stream? Now let's think about this. If we compare water and oil, okay, water, which one has a bigger refractive index? Okay, of course, the oil stream. Now, oil stream has the bigger refractive index. If the oil has a bigger refractive index, because remember, oil is optically more dense than water. Okay, dia bukan kurang tumpat, dia lebih tumpat secara optik, optically more dense, okay, than water. It's harder for light to go through oil than water. So because of that, it has a bigger end, so the critical angle will be smaller. Now, bayangkan in the situation before, critical angle of water is 46.6 lah. also can be internally, reflected. So if it is oil, the critical angle is even smaller. Okay, definitely there'll be much more total internal reflection. So the light beam will experience total internal reflection more times. Okay, because it's so easy to reflect. Okay, remember, the smaller the critical angle, the easier it is for total internal reflection to happen. Okay, so finally, this one. Diagram shows this one. If you have a critical index, uh, refractive index of 1.49, you can calculate the critical angle only by using this formula. Okay, don't have to use the other three formulas that you design because we know the critical angle. Okay, of the four formulas to calculate the refractive index, mau kira N bahkan, ini yang paling senang because you only need one thing, which is the critical angle. Okay, so when you have done this, okay, you calculated N equals to 1 over sine C, then you get 1.49, you get the critical angle is 42.2. So the critical angle of the prism is 42.2. So then you can calculate. Okay, complete the path of the light ray. Okay, so let me explain to you what happens over here. So when light travels over here, bila dia sampai sempena ini, because it is 90 degrees, so nothing happens, you just go straight through. But coming over here, okay, if you calculate these angles properly, we find that this angle 45 is the same as this angle 45. Okay, now since 45 degrees is bigger than 42.2, so it will be totally internally reflected. There will be no refraction because the angle of incidence is bigger than 42.2. So reflected over here, then you draw another normal over here, then you calculate the angle is also 45 degrees. So therefore, it will be totally internally reflected once again. So we find that ting, ting, ting over here. Okay, so that's how you complete the path of the light ray. But you need to make sure that you follow the rules. Number one rule is, if the light ray is traveling 90 degrees to the boundary, okay, then the light will just pass through. But the moment it hits at a certain angle kepada sempadan ini, okay, then you need to draw the normal and then calculate the angle. If the angle is bigger than the critical angle, then it will be reflected. If the angle is smaller than the critical angle, then it will be refracted. Okay, it will be refracted this way. Okay, so we need to know how to draw the path of the light ray. And later you will have one exercise that will help you to do so lah. Okay, now I'm just going to talk about the natural phenomena a little bit. Although this part actually is supposed to be handled by one group yang akan buat itu Google site bahkan. Okay, so anyway, one of the natural phenomena that is caused by total internal reflection is the formation of rainbow. Okay, so this is the thing that sets us apart, that sets physics apart from when masa kamu belajar sains like tahun 4 atau tingkatan 3. Okay, tingkatan 3 we only learn reflection. Okay, oh kenapa berlaku ini sebab pembiasaan, pantulan. Okay, because of but for us, we know that rainbow is caused by 3 different things. Number 1 is caused by refraction. Then after that, dispersion, okay, sebaran, and then total internal reflection. Okay, there are 3 things actually that happen, okay, when a rainbow appears. So the next time you see a rainbow, remind yourself, okay, what are the 3 things that happen and that cause the rainbow to happen? First, the light has to be refracted. Secondly, the light has to be dispersed. And thirdly, the light has to be totally internally reflected. Okay, so I will talk about this. The group that is going to this one will talk about this another time lah. Okay, another one is called the mirage. Mirage dalam bahasa Melayu, can't remember. I think it's called logamaya. Logamaya. Okay, so the mirage is like how, let's say on a hot day kan, then you're on the road lah. Kalau kau di atas jalan raya kan, then you see at the end of the road seperti ada satu kelopak air. There's like a puddle of water in front there. Okay, but actually it's not a puddle of water. When you go nearer, you see, oh, hilang sudah the puddle of water. Okay, so that's actually what we call a mirage. It's like it's like an optical illusion lah. Okay, you see something that is not there, but you see something as if it's there, but it's actually not there. In Tom and Jerry cartoons, is a bit over the top lah. But the mirage is like, wah, he's in a hot desert and then suddenly di depan dia nampak satu oasis. Okay, ada pokok kelapa lah, ada air lah, and then he wants to go and drink water lah, cause it's very, it's very hot in the desert. Bila dia sampai di sana, then dia lompat mau masuk ke dalam sana, then totally the whole thing disappear. Okay, so that's what we call a mirage lah. Okay, so I don't know whether you watch apa itu? I don't know whether you watch Tom and Jerry cartoons lah, but that's how I remember it lah. Okay, he sees a lot of mirage lah. Okay, but that's another application of total internal reflection. Okay, how is it? Actually, it's combination of two lah, refraction and total internal reflection. You cannot actually talk about one without the other. Because if you remember the situation we saw just now, whenever light travels from more dense to less dense, two things must happen. Reflection a little bit and refraction. When there's no more refraction, then everything is totally reflected. Okay, so dia memang sangat berkaitan lah. Okay, another one is Prism Telescope, Prism Periscope. Okay, Prism Periscope is the one that we use. Contohnya kalau kamu mau spy di rumah orang kan, and then so bad. Okay, and then but there's a wall over here, or in a submarine. Okay, we use periscope also lah. Okay, to see what's on the surface, especially if the submarine already submerged in the water. Okay, this is the one of the applications, as I said just now, optical fibers. So go and read up, okay, and of course the group that is doing this Google site can start doing lah, okay, and then of course the cat's reflector, not cat, sorry, cat's eye reflector, okay, not cat. Cat's eye reflector is the reflector that we use in car, okay. So go and take a look. You know what's a cat's eye reflector, right? Sometimes you see on the road over there, okay, then di atas yang garisan yang double line itu kan, you see all these small things. And then if you run over it, then you dung 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 lah. Okay, but basically those things on the road there, those are called cat's eye reflector. Okay, it's supposed to tell you that, okay, guys, don't come here. Okay, because the lights from the car will hit the reflector and then it will come back towards your eye. Okay, totally internally reflected. Oh dear. Okay, so anyway, this is yeah. Anyway, I'm waiting for the people who doing the Google sites lah, okay, to do this. All right, so that's the end of our lesson today. Wow, I've spoken for almost entire hour. So your homework will be given to you in the Google Classroom. It will come out in about 5 minutes, but basically it's page 250. Okay, question 1 and question 2, and I would like you to finish it today. Okay, because tomorrow we have another big subtopic which we want to go into. Just to remind you, tomorrow our class is double session. Number 1 at 9 o'clock and number 2 at 11:30. Okay, because I want to replace last week's class. Okay, so please finish the exercise today. Okay, yeah, today. Who said this the last time? Iqbal kah itu. Today is my birthday. Okay, so I will see you all tomorrow. If you have any questions, don't hesitate to ask, and I will see you in the next lesson.